Hello guys, last stream of the day. We're continuing with the fuzzy deduplication. Let's share the link here. Give me a second. Whoops. Continuing on with the investigation of fuzzy dedup. Okay, and turning on the live chat, let's go on. So let's first see whether NLLB paper used fuzzy deduplication at all. Fuzzy is not mentioned anywhere. Deduplication is only mentioned a couple of times. I think this was for LID. This is for the training, I think. Let's see. Okay, let's see what I say here. Okay, this is all just exact deduplication. Let's continue. I think that's it. They don't really have any mention of fuzzy or min cache or anything of that sort. Min cache, cache tags, and 3 surnames and names. Okay, that's it. So that's an answer to that question. So NLLB did not use fuzzy apparently, at least not mentioned in the paper, nor I can see it in the pipeline, in the filtering pipeline. So let's continue with the fuzzy dedup exploration. Let's skim through these papers that use fuzzy. So this is, I think, the paper behind the dataset that is behind the Falcon LLM, recently released Falcon. Fuzzy is mentioned here multiple times. Let's see. So the pile, the duplication was fuzzy, 10% removed. A pile also used and GPT-3 used. Okay, let's see. They also used exact and fuzzy. Okay, let's kind of read through this. The duplication removes repeated extracts and documents from a data set. These could either be exact matches, identical in every character, or approximate matches based on some similarity metric. For exact duplicates, it is common to match exact substrings of a minimum length using a suffix arrays. For fuzzy duplicates, methods based on locally sensitive hashes, such as min hash or sim hash, have been adopted for the pre-training data of large language models. Recently, this work has proposed to leverage embeddings for pre-trained models to imbue semantic understanding in approximate matching algorithms. The duplication has been identified as playing a significant role in improving language models. Notably, it reduces memorization, which is especially problematic in large models. Furthermore, repeated data has been shown to be increasingly harmful to model quality as parameter count increases. For a 1B model, 100 duplicates are harmful. At 175B, even a few duplicates could have a disproportionate effect. Concurrently to this work, the PTS suite of models found that deduplicating the pile had a limited impact on zero-shot performance, questioning whether dedup is as relevant for curated corpora as it is for predominantly web-based datasets. We provide an overview of some widely adopted existing pre-training English datasets with additional information. Okay, focusing on building a large-scale high-quality web pre-training data, so we extend upon the state-of-the-art. Okay, let's go. Let's see for further mentions of fuzzy. We combine both exact and fuzzy. So after fuzzy, they go from 23.30 of the original to 14. Okay. URL, text instruction, language identification. They use what? They use the classifier from CCNet. Thresholding on top language score. Curious to hear a bit more about what they've done exactly. With suffix arrays. Okay, I heard of suffix arrays method that it makes it easy to run this in linear time or whatnot, but we are not using it at the moment. Okay, let's continue reading. After filtering, although data has been improved, a large fraction of the content is repeated. Okay. We adopt an aggressive dedup strategy, combining both the fuzzy document matches and exact sequences removal. We remove similar documents by applying min hash. We compute a sketch and measure its approximate similarity with other documents, eventually removing pairs with high overlap. Min hash excels at finding templated documents. Licenses with only specific entities differing placeholder SEO text repeated across websites. See examples of the biggest cluster in appendix H1. We perform min hash deduplication across using 9,000 hashes per document, calculated over 5 grams, and divided into 20 buckets of 450 hashes. We found that using less aggressive settings, such as the 10 hashes of the pile, resulted in lower deduplication rates and worsened model performance. See the appendix G31 for more details. Okay, that was fairly detailed. Exact substring operates at the sequence level instead of the document level. Finding matches between strings are exact token by token matches by using suffix array. Can we actually do fuzzy for? It seems they're all doing it on document level, whereas we have paired sentences, so it's not clear. We know that exact substring alters documents by removing specific spans. We also experimented with dropping entire documents or making the duplicated strings instead of cutting them, but this didn't result in significant changes in zero shot. Okay, let's continue. Let's see the G32 section. Okay, just a second. Okay, and in a comment, combine both exact and fuzzy. Okay, fair enough. Let's continue. Is this G31 section? F3 datasets. Okay, we're gonna check that. Let's see what this is. Okay. And that's it. So G31. Wait. And there's some mention here, I think, was it? Okay. Here it is. Signing, matching, exact substring deduplication, min hash. We employ min hash to find approximate duplicate documents in our web corpora at a very large scale. This technique allows us to identify templated pages or otherwise very similar content, blah blah blah. Where most of the interspersed duplicated sections are small enough to not be identified by exact matching methods. We start by normalizing the content to increase recall. Punctuation is removed, text is lowercase, NFT Unicode normalization is applied, accents are removed, and all white space is normalized. We tokenize the resulting text using the GPT-2 tokenizer and obtain the set of unique n-grams for each document. Hash functions are used to obtain a signature for each doc. For each hash function, the smallest value is kept from caching every unique n-gram in the document. Okay, the ratio of matching caches between two documents approximates the checker similarity of the sets of their unique n-grams. Since comparing min hash signatures between every single document pair is computationally expensive, we apply a locality-sensitive hashing version of min hash. A document signature is split into R buckets, each with B min hashes. Documents are indexed by these B min hashes on each of the R buckets. And we mark two documents as duplicates if their B min hashes are exactly the same on at least one of the buckets. Okay, for two documents I and J, whose ratio of matching hashes between their min hash signatures, the probability that there is a match in a given bucket is S sub ij over B. The probability that there isn't a match in any of the buckets is this. And finally, there is a match in at least one of the buckets is this. We use the same parameters as this paper, 520 and 450. Okay. Finally, we cluster documents across all buckets. If documents A and B match in one bucket and B and C in another, ABC becomes a cluster. We randomly remove all but one of the documents in each cluster. Okay. So this previous work also proposed filtering down false positives by computing the real Jacquard similarity or other metrics. Okay. So let me just make some notes. So for fuzzy dedup, C refine web benur big file, etc. This one also mentioned we calculate the Levenstein distance. This is for this is parallel corpus. This might be super relevant for us. Whereas the previous one was just a mono corpus. Okay. Continue. Let's go. Fuzzy. Parallel corpus whose cleaning is undertaken in the study CC matrix by Opus for Japanese Bulgarian. In its original form, the corpus contains 4.1 million sentences. The corpus contains a little over 2.5 after some pre-processing. The test and validation sets of the translation model comprise 1,000 clean parallel sentence pairs. Continue. You guys are not using mid-cache, as far as I understand. There isn't this Levenstein distance. Very complicated to understand. Okay, then I don't know. I think if you just spend some time, you'll probably understand it easily. Classifier model. Noise in the corpus. Non-corresponding numbers and dates. Inappropriate punctuation. Wrong use of abbreviations. As numbers and dates widely mismatch between the two languages within a sentence pair, they are regarded as noise. The next largest source of noise is the Bulgarian sentences. It comes in the face of problems with punctuation. However, one disregards the lack of final punctuation with these fragments, they read smoothly and match unproblematically between the two languages. Here, one Bulgarian sentence contains the word sorry. Seemingly machine translation sentences come at as much as closely 5% and are therefore placed in a separate category. Foreign language within a sentence ranges between a single word or phrase that can safely be regarded as a proper noun and a full sentence written in a foreign language with a few seemingly mistakenly inserted Bulgarian words. Yeah, that's what I noticed as well. Numbers and dates are never correct in the mine data, which makes sense. Okay. From mine datasets. Like the majority of submissions of WMT's corpus, filtering shared data study starts off with a pre-processing step that applies a series of heuristic rules to the noisy corpus. Okay, and not answered entries and duplicates are removed. Why is this a thing? Sentences in different languages are removed. Japanese sentences are tokenized. Dates are replaced with the tag date. And numbers are replaced with the tag num. The library date finder is utilized to locate dates written in a variety of formats. Yes, we also want to change the length ratio, currently 9, and probably also low min max lengths. Okay. Dates. Tool used to identify sentences in languages other than the expected ones is lang detect. Isn't that one? Okay, lang detect is not as good as far as I know. Convenient in the case of short amounts of text. Language is labeled in accordance with a large portion of text, thus allowing for sentences with words and phrases in English that take the role of proper nouns to remain in the corpus. Several patterns of wrong labeling are established and taken into consideration. Also, even though the latter utilize neural models do not mandate prior tokenization, a decision is made for Japanese text to be tokenized as part of preprocessing due to the language's notorious lack of space delimiters between words. Proxy filter classifier. This study sought to apply a winning state-of-the-art model from the WMT corpus just skimming this part. After the CC matrix corpus was preprocessed, subcorpora were obtained through the application of three techniques. Results. Okay. Maybe skim through this document, this blog, just to get a bit more context on this. And I think after this, we don't really have, we just need to start pushing our data through the pipeline. Yeah. Okay. Practical concepts for detecting near duplicate documents, followed by a Python sample. Let's just swim through this. Okay, optical character recognition could include small noise, and thus you could miss almost completely identical pieces of text. Minor revisions and drafts. Stray punctuation, capitalization, white space. Okay, there's some task on Kaggle. Folks submitting ads often make tweaks to their existing ad and resubmit it to have a higher chance of people finding their product. Quick trip to Craigslist shows us an example of this right away. Executing a simple exactly equal script like we described above, we see that about 96,000 of these ads are originals, not an exact duplicate. There are about 1,000 ads that are exact duplicates. Most duplicated advertisements. The new sheepskin leathers coat with natural fur. String similarity with cosine distance. Watery. Let's take a simple count of each time a word occurs in each of the phrases. Okay, this is sparse. Engrams. This is just nothing new here. Stemming. Document term matrix. One important area for consideration is the cosine similarity threshold we choose. Remember, when we compare two document vectors, we'll get a cosine similarity between 0 and 1. It's up to us to decide whether the result passes or fails. 0 would flag everything is duplicative. 100% would require exact duplicates. The plastic documents were flagged. When you're true duplicates. Okay, definitely a less relevant article. Okay, this Stanford presentation seems to explain the whole thing. Let's just skim through it because there is too much. Shingling. Simple approaches. Set of words appearing in the doc. Set of important words. Example. Yeah, on the high level, it's not complicated. Sequence of k tokens that appears in doc. Tokens can be characters, words, or something else depending on application. Assume tokens are characters. Here we have shingles A, B, B, C, C, A. Present the document by a set of hash values of its k shingles. Like a good document. Just gonna put it under the literature or and then the LSH. Okay. Let's see what we could use in practice. Okay. What are people complaining about here? This is how to use it in practice. Yeah, we can always find about theory if we want to, but let's first see how to use it. Hello there, what's up? Awesome, glad to see you. Nice work on the README, thank you. Awesome, glad to hear that. There is still a ton of things to improve because currently it's just fair-sec. We can create it as a sub-module or something. We'll see about that a bit later. Thank you. Okay. Set 1. set 2, set 3, min hash 1, 2, 3, for element in the set, we encode and update. So we have 3 sets, and then create the LSH index. LSH insert M2 and M3. We can try this example. Thank you, thanks a lot. I really appreciate it. I really love what you do. It really brings passion to contributing and doing a great project like this one. For inspiration. Thanks. By the way, if you didn't see it, just FYI, I'll be going to China tomorrow. So that's gonna slow down the streams. I won't be doing the streams over the next 7 to 9 days actually, until 26th. But after that, I'll be fully back doing the streams. But even during my trip, I will definitely be engaged in the server. I'll be working as well, just a bit less, just because I'm in China. Just FYI here. Okay, I'm gonna try out this piece of code just to see how it works for byte text that we are using. Thanks. Okay, the Jacker similarity threshold must be set at initialization and cannot be changed. So does the number of permutation functions. Similar to min hash, more permutation functions improves the accuracy, but also increases query cost. Okay, I experimented with 20 news group datasets, which has an average cardinality of 193 of 3 shingles. The average recall precision plotted below. See the benchmark directly in the source code repo for more experiment and plotting code. There are other optional parameters that can be used to tune the index. See the documentation. Does not support top K. May not be the best measure if your intention is to find sets having high intersection. This is if you want to use databases. Cassandra as well. Connecting to existing min hash. Asynchronous min hash, LSH scale. When you're using RESTful API. Let's see, what is this? Mongo. Common issues. Memory and on-disk size. Okay, let's see what people are seeing here. It's a learning journey here. Okay, so that's one project, and then there is this one, text dedup. What's the difference between this one and these ones? I like these charts. Cool. Ton of cool resources. Data sketch. That's the one we just looked at. And then there's this one. For some reason, there is some duplicates. One of the papers I opened up linked to this one, to this code base. I don't remember which paper exactly. You refine web. I think it was refine web. Refine web paper. Not really. Or maybe Nordic file. I think it was this one. Yes. They use this particular code to dedupe Nordic file dataset. Just see what parameters they use. We use 10 hash functions. Okay. Let's see this code. random seed, pairwise list of the input files and keys. Fingerprints, Jacquard. So apparently, here are some of the options we have. Let me just write them down. So for fuzzy dedup, resources, and then this one. Okay. So let's try this one. This one looks like the simplest. Something we can try fairly quickly. I'm curious just how did people parallel corpus cache? How do people do that for small? Or machine translation, min cache, deduplication. Just if we use a single sentence, will that work nicely? Chris. Thanks, man. And just try something locally and see how it works. So let's just grab this. Let's pip install this thingy. Okay, let's see. We are in data. Let's just split them. Let's see how this works. Query, and then we say query M1, and then it says approximate neighbors with Jakarta similarity, M2 and M3. What? That's not really useful. Aha. Okay. So let me just think for a second. So they are emulating, like, this set is basically, okay, so for us the set could be a sentence. Let's try something practical. Let us grab some corpus that we have, like, let's grab Serbian. Let's grab something a bit smaller. Maybe Tatuiba, let's see. How big are these? 10,000, that's fine. Copy the path and go back to okay. So English path is going to be this, and then Serbian path is going to be this, and then English lines, and then Serbian lines. Fair enough. And then what we want to do is let me see. We're asking for duplicates. Okay, let's see. Let's basically create a ton of these. So we go for Serbian line, English line. We strip it. We construct a set like this. Not exactly. It's going to be how should we do this? Something like that, and then plus English line split. And then for D in set 1, M1 update. I don't really know how this is used. Would be cool to, I'm trying to just infer how it's used. Would be cool to see some examples, because min cache is a probabilistic data structure for estimating the similarity between data sets. So we're just adding a ton of these. Why would we what does update mean here? I think for us this is just in cache. Is it? Why are they encoding it? What's up, Nicola? So we update with this, and then I think we're using it incorrectly. We probably need one for each of the sentences. Yeah, I think we need one for each of the sentences, basically. Update, and then we need one of these. LSH, and then we're going to be inserting the LSH. Insert we can do something like I have no idea if I'm doing this correctly. I'm kind of guessing how stuff should work. Okay. I keep on inserting, and then at the end I'm going to query. That's how I understood it. So we can comment out all of this. We don't care about these. So we create min hash, a ton of min hashes. We insert them into the LSH. Key, a unique identifier of the set. Exactly. And then at the end, let's try stuff like, let's try, so I'm using Tatuiba. So I'll just pick something like, I miss you. Let me just put this on the right. Open the English. So you can just modify this. Okay. Let's see. Oops. Print return. That would be interesting. I want to see what print returns gives us. Okay. Let's read this. I have no idea what's the time complexity. I have no idea. I'm just using some arbitrary thresholds at the moment. Nothing is optimized. Let me also add the PDM. Rerun. Okay, it seems this looks very fast. And nothing. Okay, interesting. Let's try this. Or let's try a couple of them. Queries. And then exact one. Okay. Oops. Okay. Fair enough. And then yes, we create a min hash, and then we query and see where we get results for any of these. If we don't, then something is off, or I have to potentially change the number of these permutations and stuff. I think this tells us how rich the signature is, this 128. We use 128 hash functions in the background. Nothing for the first one, nothing for the second one, nothing for the, yeah, this is, something is not working. Why am I even doing this? We don't need that. Printing this. Maybe we need to set something. Not sure. Let's see. Run. Ah. Okay, I messed up. Messed up. Let's go. Let's just run. Just let it run. Okay. I am expecting to find some results now, at least for some of these. Oh, snap my life. Not really. Let's see again. Why is this not working? If we enter here, let's try something. I pravo nešto. I miss you, nedostaješ. I literally have the same one. Maybe we need to specify what the threshold is actually fairly low. Let's reduce it. I think if we put 0.1, we're gonna keep on retrieving various different things. Let's see what we get. Maybe let me just comment this out. Let's now run this. We should now be catching various things. Let's see. Even noise. But we're not, okay. Nothing. Okay, let's try and step through this a bit. We don't probably have to change the cache function or anything here. This is advanced. We just need to change one of these two. Here. Two. Only two buckets. I mean, yes, I could be analyzing all of this, but I don't really know. I'd have to read a paper or two just to get some just to become a bit comfortable with all of these arguments and what they exactly do. I did expect maybe we need to, after all, do some type of splitting here before we update. Let's try this. So go through the words there, update. Okay, and then here the same query. Word encode. And only then ask, right? If we have two sentences, they're stripped. We combine them, we split them, we go through the words, we cone those. Then we put that inside of here. And then same here. Let's try this. Run. Ah, this now works. Although it's shitty because I've put a very, very low threshold. So let's try, let's go 0.5 here. Let's rerun. I'm a hacker myself. Opa, nice. 0015 was exactly the one, guys. This was the this one, the I miss you. So this one was matched properly only with this one. That's amazing. Okay. So now let me see. The second one should also be matched with 15. Yes, and nice. All three were matched only with that one. That's great. This is fuzzy deduplication without us understanding how it actually works in the background completely. Like I know the theory, but I don't have all of the pieces combined into a broader picture. I would have to understand a bit better how it works exactly. But here it turned out we don't even need to do that. So now what I want to do now is, now that we've put everything into the LSH, so now I would love to go to the sentences and see whether any of them has more than one match. In that case, we found duplicates. So let's see how many of those we find. So now let's go and do the following. Not the queries, but go through the sentences again. Do the same logic. And then query. Okay. So again, we go, we build, and we query. And if the result, especially if the length of the result is bigger than 1, we want to print the result. Print what? Print I and print result. But we want to parse result as the integer. So that means, well, we might not be able to do that if it's a, it can be array. So basically I is basically a duplicate of all of these other ones. Let's see. Will we ever hit this? Who knows? Let's try. Okay, for the zeroth one is, okay, so this is a list. So if it's a list, we can do the following. I and then we do something like, let me see. Something like this, and this gives us a list of integers. Yeah, I think this was going to be readable enough. Okay, let's go. Ah, nice. So 4 has a duplicates on line 4015. Shifre Muriel. Let's find this one. Hopefully it's not the exact duplicate. The password is this. Now if we go to 4015, 4015, we must be new here. Nah, this is not good. Or let me see, maybe am I using the right indexing? No, I'm not. So 4 basically means I will be back soon. Vraćam se uskoro. And then we do Tom bi morao da se vrati uskoro. Aha, this is fairly similar there. Tom may be back soon. It's kind of similar, not quite the same. Tom may be back, and here I will be back soon. Okay, with some tuning, this will become reasonable. For now, we're just playing. Let's see. Eight. Okay, let me just improve this a bit. So first of all, we don't need a TQDM. It's ruining our output. Remove all this. Secondly, we need to add +1 and +1 here as well, because oops, that's how VS Code is rendering line numbers. And now we can also say if element is different than I. Okay, so if it's different than this here, then we mention it. Okay, just to clear it up a bit. Let's go. Five has duplicates on lines 4016. We just remove this as well. Let me see how we can do this, make it a bit nicer. Okay. Now we can check this side by side. Five has duplicates online. We've seen that one already. Let's see. 9 on line 5371. I was in the mountains. Bio sam u planinama. 5371. I was in Rome. Okay, not quite 5731. Ovaj članak sadrži neke... Okay, this is... Oops, this is bad. 5371. Bio sam u Rimu. Not quite. This is a false positive. 12 has a duplicate on line 3421. So 12, which is you are in my way. 3421. You are in my spot. 3421. Fairly similar. Let's make it a bit more rigorous. A bit more rigorous. Let's put it to like 0.6. Again, I have no intuition, or 0.7 or 0.8. If it's like really similar. Let's say 0.7. 5. Okay. Let's run this. Let's see when do we get to a duplicate, a fuzzy duplicate. Okay, 61, so it took a bit more. 62 has duplicates on line 63, interesting. Let's go and see. 62, aha, I can't live without a TV. This is exactly duplicate. 62, nice, they are kind of duplicates. This was great, this works, guys, this just works. Let me take a screenshot, share it with people in the server. So English was exact duplicate, but on the Serbian side, it was fuzzy. Like TV or yeah, television. That would be English translation, I guess. Kinda. Because television is like TV device or something would be. Let's find the next ones. '67 also on line 69. What do you want? These are also similar. Let's go. Ha! They retrieve only a single one apparently, and then we need to. That's why we would need to put back Oh no, they actually retrieve more. Let's see. Let's try a couple of these. This one, and whoops, and here as well. Please wear a mask. Please wear a mask. And then it mentioned 6, 5, and 4. Exactly. Guys, this is just amazing. That's what we need. None of these would be matched with our... Maybe some would be matched, but we would not match this one. So we would be left with some duplicates. Okay. So we got something running. We got something running. It seems it scales very nicely as well. Like, let's try a bit bigger data set. And then we can learn a bit more about parameters and try and get this integrated into our filtering pipeline. That's going to be the easy step. The hard step will be understanding. Well, we can. It can't be that hard. There's only a couple of hyperparameters, and some people probably know this better than I do already. So we can just reach out for help. Let's see. Let's grab something a bit bigger, but not super big. Like, what's the size of this one? This is a good example. Let's try. This is 20x bigger. What's the runtime of this thing? It's gonna be the runtime. So if we pick now this versus this, like English Latin and Serbian Latin, how long would this take? Probably not a lot, because this is just not that much really. These are usually used on much bigger scales. See? Okay, this is creating the LSH. I mean, even if it was 24 hours, it would be fine. If we won't be running this too often. We'll figure out the hyperparams and then we'll just kick it off once and that's it. Okay, let's see. So far it looks like for 100K, it's around a minute, which is not really promising because we have millions of sentences. So even slower than that. Let's see. Although bear in mind this is unfiltered data, which means we have some very long sentences, etc., etc. Not really fast. I like this TQTM progress bar. Makes you feel like you're being productive. Even though you're not really. You're just looking at a progress bar. Like watching the loss curves go down. A couple of joys in life. What more can you ask for? It's little things in life. Wait, stop. There is a ton of these. I want to check this one. What's up with this one? Copy. Open this up. Split right. Open this up. Split right. Let's find them. World Press Freedom. Really? That's gonna be that big of a duplicate? Oh no, that's not. Wait. 6586, okay. And then apparently World Congress closing ceremony. Not quite. So we'll have to watch and set the right. We probably have terrible parameters set now for this big one. Like for example, the refined web. So these guys use only 10 functions. That's not that much, but refined web paper used like 9,000, was it? Was it 9,000? 5 grams. Beef 20 R450. Can we just set B and R directly instead? What threshold do they use? B20 R450. Let's see whether we can set that ourselves. LSH. (09) params. Yes, we can just set the params. Let's do it like that. So let's just set params to the same number that these guys use. Like params should be B20 450. So B should be 20. Okay, so let's Let's try this one. It's gonna take a while. Number of permutations. Run again. Okay, we're trying to insert now these ones, but they are okay. It's gonna be probably even slower, considerably slower. Okay, yeah. Again, this is that trade-off. How much time, how much compute, what's the recall you want, can you tolerate false positives? All of those questions need to be answered, and to be able to properly answer those, you need to understand a bit, or have somebody who understands it, or just, I don't know. There are quicker ways to do this, apparently. What's the collector? Using Redis as a storage layer. read a bit about how this works. Chris mention anything about data sketch? He did. I don't think it's academic. I mean, it looks like it's a package. Linecone, that's the vector DB. They use obviously LSH in the background. I think we shingled using just splitting, which is probably not the optimal one. We should have passed in engrams or something. So currently what we're doing here is we're literally just taking words, and that's how we are shingling the quote-unquote document, or sentence in our case. Actually the pair of sentences, source and target. But we actually need to do something. There are probably more optimal ways to do this than just this. Oh, this looks good. Looks like a very nice explanation. I think if we read this, we'll probably understand how this works. We probably don't need to read any papers or anything. This will probably be enough. And then this one. Let's see how this is progressing. 11%. Wow. Very slow. I say let's read this and this block, and that's it for tonight. Let me just see. These 3 videos might be also good. Okay. Let me just quickly stretch my legs and then we can start reading this article. Just need a bit of a break. My mini break, and we are back to reading about LSH and Mincache. break. 3 minutes stretching. Be right back. Okay guys, catch you in a couple of minutes. And we are back. Okay. Let's go. Let's read this. Locality sensitive hashing. The illustrated guide. Just some random intro, we can skip all of this. Okay. Let's see. Imagine a dataset containing millions or even billions of samples. How can we efficiently compare all of those samples? Okay. We want to go sublinear. Should be like log n or something. This is very much relevant to vector DBs. I mean, pinecone being one after all. Shingling, min hashing, and the final branded LSH function. This is what we want to do. At its core, the final LSH function allows us to segment and hash the same sample several times. And when we find that a pair of vectors has been hashed to the same value at least once, we tag them as candidate pairs. It is a very similar process to that used in Python dictionaries. We have a key value pair, which we feed into the dictionary. This is how it works in the background, the vector DB. We have a key value pair which we feed into the dictionary. The key is processed through the dictionary hash function and mapped to a specific bucket. We then connect respective value to this bucket. A typical hash function aims to place different values, no matter how similar, into separate buckets. So this is your Python dictionary. If you have like a key, like a string, you hash it internally. It gives you an index to an internal table, and then you map the values there. That's your typical. I mean, this is taught in algorithms classes, computer science stuff. In LSH, the goal is almost opposite. We want to maximize collisions, although ideally only for similar inputs. Indeed, they all share the same bucket, similar samples through a hash function logic, but they can vary a lot beyond this. That's something that person building VectorDB would say to prevent the competition from trying to do the same. The method we have briefly described there are several other techniques such as random projection, which we cover in another article, shingling, min caching, and LSH. The LSH approach we're exploring consists of three-step process. First, we convert text to sparse vectors using k-shingling and one-hot encoding. Then we use min hashing to create signatures. So our shingling is basically splitting the words, splitting the sentence into words, using the space as the delimiter, which are passed on to our LSH process to weed out candidate pairs. Okay, shingling does this. This one hot might happen inside of the package we're using. And then we get a min hash. And then band and hash. find candidate pairs. Okay, k-shingling. Converting a string of text into a set of shingles. Shingling also removes duplicate items. Hence the word set. And I think that, if I recall correctly, DefineWeb used 5 gram shingles or 5 shingles. $5. Yeah, I think that's it. Okay, so what I do here, shingle set, given text in K, we append K shingles, and we return a set. And with this, we have our shingles. Next, we create our sparse vectors. All of our shingle sets are merged to create our vocab. We use this vocab to create our sparse vector representations of each set. All we do is create an empty vector full of zeros and the same length as our vocab. Then we look at which shingles appear in our set. Clear? To create our one-hot encoding, our single shingle set is matched up to our vocab, which indicates where in our zero vector we should place ones. We use a shingle to index dictionary in our code. For every shingle that appears, we identify the position of the shingle in our vocab and set the respective position in our new zero vector to 1. Some of you may recognize this as one-hot encoding. Well, this is not one-hot encoding because because you have multiple ones in the vector. For one-hot encoding, you need to have just a single one. One hot. Hot being, this comes from electronics, by the way, because when you have one, that means that's like voltage high, there is current, it's hot. That's why it's called one hot. Fun fact. Today I learned. Okay, min hashing is the next step in our process, allowing us to convert our sparse vectors into dense vectors. Now, as a pre-warning, this part of the process can seem confusing initially, but it's very simple once you get it, as all things are. We have our sparse vectors, and well, n-gram is just a number of characters. Like if you have 5 gram, that means 5 characters. So this would be a trigram of this sparse word, or this PAR, or ARS, or RSC. Those would be all of the possible trigrams for this word. That's it, nothing fancy. Worries. We have our sparse vectors, and what we do is randomly generate one mini hash function for every position in our signature. For example, the dense vector. So we have our sparse vectors, and what we do is randomly generate one min hash function for every position in our signature. So if we wanted to create a dense vector signature of 20 numbers, we would use 20 min hash functions. Okay, so that's the, I think that's the number of permutations, the argument in the package we've been using. Okay. Now those min hash functions are simply a randomized order of numbers, and we count from 1 to the final number. Because the order of these numbers has been randomized, we may find that 1 is in position 57, for example, of our randomized min hash function. Okay, our signature values are created by first taking a randomly permuted count vector and finds the minimum number that aligns with a 1 in our sparse vector. Above, we're using a smaller vocab containing 6 values, so we can easily visualize the process. We look at our sparse vector and say, did this shingle at vocab 1 exist in our set? If it did, the sparse vector value will be 1. In this case, it did not exist, hence the 0 value. So we move to number 2. Identify its position and ask the same question. This time the answer is 1, is yes, and so our min hash output is 2. That's how we produce one value in our min hash signature. We need to produce 20 or more. So we assign a different min hash function to each signature position and repeat the process. I'm gonna slowly go through the diagrams again. Let me just quickly skim this. Here we are using 4 min hash functions, vectors, to create a 4-digit signature vector. If we count from 1 in each min hash function and identify the first value that aligns with a 1 in the sparse, we will get 2, 4, 1, 2. Okay. This is going to be such a great article, I think. Really nicely visualized. Let's see this. Let's just watch this a bit. We shuffle the list. Okay, so this is our vocab, and then we shuffle, and then we say is vocab of 1. Let's see again. So this is our sparse vector, which is a shingle. Aha. Let's watch this just a bit more. It would be cool if we could slow it down. It would be super cool if we could slow it down. So we shuffle 2, 1, 3, 6, and then vocab of 1 equals 1. I don't get it. It's too fucking quick. Right, it's fast to grasp. Let me try. Grab a couple of pictures. Well. Why is it 2 exactly? Because So we have, this is the vocab, we have 6, we shuffle the vocab, sure, and then we are like 1, 0, 2, 1, and that's why we put 2. Okay, so let's see. Here we have 4, 6, 5, 3, 1, 2. So we take 2. Here we have 4. Then we have 1. Then we have 2. Why? If you count from 1 in each mini-hash function and identify the first value that aligns with the 1 in the sparse what does it mean for that aligns with the 1? Okay, that's the part about randomization is that's a way for you to randomly create these hash functions. That's just, I think for now you can just accept that as given. Let's go through the code. That might make things a bit easier. So here's the hash, and then we shuffle, sure, and then loop through this randomized min hash vector, starting at 1, and match the index of each value to the equivalent values in the sparse vector A1 hot. If we find 1, that index is our signature value. Okay, so 7, we basically ask where in the hash function can we find what's the index of the number 7, and it gives us 1, so 7 gets mapped to 1. Okay, we now have a randomized list of integers which we can use in creating our hash signatures. What we do now is begin counting from 1 through and extracting the positions of this number in our new hash list, like so. So we go through the number and find what's the index of this number, 1. So index of 1 is 58, 19, 96. Okay, I think I'll need a bit more cognitive capacity to read and understand this fully. I can probably leave it for tomorrow or whenever I have some time because of the China trip. Let me think. I think I'm getting closer to understanding it. Let me just see. One. What's the... We go with 1. What's the index of 1? Should we retrieve like 0, 1, 2, 3, 4, 5, 4? I would expect to see 4 here, and then generate a randomized min cache. Okay, sure. Then loop through this randomized min cache starting at 1 and match the index of each value to the equivalent values in the sparse vector. If we find a 1, that index is our signature value. Huh. By that logic, shouldn't we be going and looking for 1 here and then find the index, and the index is 5? Hash example. Index of 7. Where is 7? 7 is at position 1. Sure, but then we now have a randomized list of integers we can use in creating our hash signatures. So where can 1 be found? Why did you wait? Why didn't you show us the whole fucking thing? Like, now it's confusing. Is this 1 found on the position 58 here, or what? Is this 2 found on position 19? We don't see none of these numbers here, and yet they use that as an example here. That's just a terrible example, if that's what you're trying to tell us. What we do with this is count up from 1 to this and find if resultant position in our 1 hot encoded vectors contains a positive value in that position, like so. So we go through that, we find the index in the hashed one, and we asked, is the signature value existent? So index gets mapped to index here, and that maps to signature value. Okay, so we go find 58. Is 58 gonna be 0, 1? Okay. And then at 98 position we obviously had 1. Let's see whether that makes sense with the above one. So, aha! So we take 1, we find the index of 1, which is 0, 1, 2, 3, 4, and then we ask, and then we ask, is at 4, is it a positive value? It is. And so because of that, why do we retrieve 2? Are we looking in the right direction, by the way? I'm assuming it's indexing from, this is 0, this is 5. Build a signature from multiple iterations 1 and 2. So create a hash function, a random shuffle, build a min hash function. We create 20 min hash vectors. So if you pass in 20 here, you go and create 20 different vectors, which you retrieve back here. And then to create the hash, you go through the mishcash functions, you go through the vocab, you find the index of I for that particular permutation, and you check whether the vector of that index was the value, and And if it's 1, then we append the index. And then we return the signature at the end. Create hash for this vector, for this vector, and for this vector. And we print. It's really nothing more complex than that. We've taken a sparse vector and compressed it into a more densely packed 20-number signature. Okay, I might get it all almost. This is the most valuable code, basically. This part here is the most valuable code. So again, we go through the min functions, we go through indices, but we start at 1 actually. And we asked, where is the index of 1? Where can 1 be found, and what's the index? 1 can be found here at index 5. So 1 can be found at index 5. And what's vector at index 5? 0. Because it's 0, we don't append it. So like having 4 values here implies we have 4 different min functions. Yes, okay, true. So this one is supposed to produce just a single number. Right? But then I don't get it. Wait just a second. We go. This could, in theory, aha, we break immediately. Got it, guys, I got it. So let's start. So we start with 1. What's the value of 1? What's the index of 1? Well, it's 5. Well, 5 is 0. More like next time. Then you go with 2. You ask, what's the 2? What's the index of 2? The index of 2 is this. Okay, 2 is actually activated, so put 2 here. Same here. You start with 1. What's the index of 1? It's here. Well, it's 0, so you have to go to 2. You go to 2. Oh, it's 0 again. You go to 3. Oh, it's 0 again. You go to 4. Oh, 4 is here. So you put 4. And same here. You start with 1. It's 1. Awesome. You put 1. And then you start here. Where is 1? Here's 1. Oh, it's 0. You start with 2. And then, oh, it's 1. So you put 2. So that's how you get. So that's how it works. Did you get it? If you're still here. That's how it works. It's not that hard. It was just confusing going through this. Now it's going to make more sense. So basically, you create these random permutations of your vocab length. So like range from 1 to vocab length plus 1. And then once you have those random permutations and you have your sparse vector, which represents your input sentence, like the shingles and stuff. This one tells you, hey, we have that particular engram in our sentence, and this one, and this one. It's a set. And then you start from 1, you find 1, and then you go from 1 to the size of the vocab until you find the first number that matches 1. So 1 does not match anything. 2 matches 1, so that's why I put 2. So you're searching 1, 2, you're looking for the first value that has the corresponding 1. That's it. And that's how you convert this sparse vector into a dense one. We'll understand it a bit better tomorrow as soon as this kind of settles down, but that's kind of the idea. And then information transfer from sparse to signature. Is the information truly maintained between our much larger sparse vector and much smaller dense vector? It's not easy for us to visually identify a pattern in these dense vectors, but we can calculate the similarity between vectors. If the information truly has been retained, surely the similarity between vectors will be similar too. Well, we can test that. We can use Jacquard's similarity to calculate the similarity between our sentences in Shingle format. Then repeat for the same vectors in signature format. So Jacquard is defined like this. We have two sets. We find the interactions between the set and then the length. That's basically the cardinality of that set. And then length here of the cardinality of the union. That's the definition of Jacquard. And then you find the Jacquard between A and B, which are the original sparse vectors. And you find the Jacquard between signature. Now, what does it mean to take a set of the signature? Do you take, that part is not clear. Aha, okay, it is, because signature might have multiple same numbers and then you just convert it into a set, okay? And here the Jacquard, there is some difference. I don't know what to make out of it. And then A and C, we see pretty close similarity scores for both, so it seems that information is retained. Let's try again for B and C. Now, what are the A, B, and C? What's the A, 1 hot and 2 hot? You just see how those are defined, if anywhere. They didn't really even define it. It's almost like going through a dream. It's not really, it's like continuous. It just jumps back and forth. And that's not a good description of something that's not supposed to be like a dream. Okay, so now we do, so like the whole point is you convert your input sentence into some dense vector, but you're not using a neural network to do that. You just use this weird mathematical set of functions to do that. If it's easier for you, you can just think of it like, okay, this embeds your input sentence into a dense vector in some way, in some, you can treat it as a black box if you don't understand it. Yes. Yosif, blue of 1, 6. So that's 1, so that's different than 0. So go to blue of, then you go to until you find 2, and then it's 1. Yeah, you got it, I think. The final step in identifying similar sentences is the LSH function itself. We will be taking the banding approach to LSH, which we could describe as a traditional method. It will be taking our signatures, hashing segments of each signature, and looking for hash collisions, as we described earlier in the article with the dictionary. Okay, so again, shingling, 1 hot using the vocab, using min-hash shuffles to get the signature. So each of the shuffles gives us a single number, because here what 3 tells us is that basically 3 was the first number in this shuffle sequence that had 1 in the sparse representation. Okay. Through this method, we produce these vectors of equal length that contain positive integer values in the range 1 through length of vocab. These are the signatures that we typically input into this LSH algorithm. Now, if we were to hash each of these vectors as a whole, we may struggle to build a hashing function that accurately identifies similarity between them. We don't require that the full vector is equal, only that parts of it are similar. In most cases, even though parts of the vectors may match perfectly, if the remainder of the vectors are not equal, the function will likely hash them into separate buckets. We don't want this. We want signatures that share even some similarity to be hashed into the same bucket, thus being identified as candidate pairs. How it works. The banding method solves this problem by splitting our vectors into subparts called bands. Okay, again, recall quickly that we have the refined web project used basically 20 and 45, 450, which means the following. R is the number of hashing functions, if I recall correctly. Let me see here whether they mentioned it somewhere. And B, do they mention it here? Number of bands, and R is the band size. Okay, maybe this might be a bit different. Let's see. Splitting our vectors into subparts called bands B. Okay, then rather than processing the full vector through our hash function, we pass each band of our vector through a hash function. Imagine we split a 100 dimensionality vector into 20 bands. That gives us 20 opportunities to identify matching subvectors between our vectors. So 3 bands in this example, subvectors, and then we hash them and we put them into some of the buckets. We split our signature into B subvectors. Each is processed through a hash function. We can use a single hash function or B hash functions, and it's mapped to a hash bucket. We can now add a more flexible condition. Given a collision between any two subvectors, we consider the respective full vectors as candidate pairs. Okay, so we start with signature A, we hash, and for this subvector they are not aligned. Here they are not aligned, but here for the third subvector, the hash function mapped them onto the same slot, and because of this, we go backwards and say, okay, B and A must be candidate pairs because some parts of them are similar. So we split the signatures into subvectors. Each equivalent subvector across all signatures must be processed through the same hash function. However, it is not necessary to use different hash functions for each subvector. We can use just one hash function for all of them. Now, only part of the two vectors must match for us to consider them. But of course, this also increases the number of false positives when we say they are duplicates, but they're not. Samples that we mark as candidate matches where they are not similar. However, we do try to minimize these as far as possible. We can implement a simple version of this. First, we start by splitting our signature vectors A and B and C. So we split the vector. We assert that they are divisible by B, and then we find R, which is the length of the signature divided by B. Aha. Got it. So this is the size of the subvector. So does that mean for us? Yeah, that means that for us, so we specified B and R, which means that we implicitly specified that we're using 9,000 hash functions. So that's why this was so slow, and it's still running, by the way, because we're specifying 9,000 hash functions. For each of our input vectors, for each of our sentences, we have to compute 9,000 hash functions to get that dense vector. And then we go through the signature with the step size R and just subvector it. Okay, split into 10 bands, repeating rows of 2. Split, split, split. And we end up with what? We end up with band B being two times 10, if they were 20 originally, or what? Then we loop through the list to identify any matches between subvectors. If we find any matches, we take those vectors as candidate pairs. So we loop through the bands, and if they are exactly the same, then we break. But where is then, we didn't do any hash function. And let's do the same for A. We find that our two more similar sentences, B and C, are identified as candidate pairs. The less similar of the trio, A is not identified as a candidate. This is a good result, but if we want to really test LSH, we will need to work with more data. That we have built this, what we have built thus far is a very inefficient implementation. If you want to implement LSH, this is certainly not the way to do it. Rather use a library built for similarity search like FACE from Meta, or a managed solution like Pinecone. But working through the code like this should, if nothing else, make it clear how LSH works. However, we will now be replicating this for much more data, so we will rewrite what we have so far using NumPy. Semantic text similarity task. We'll be extracting a set of sentences from here. Okay. The confusing part, I think the part that they didn't do service justice to is this part. They did chunk into sub bands, but they didn't show us this hash function additionally. They just compared the bands themselves directly. You see, they add sub vectors, and then they just compare the rows directly, which is not only inefficient but also incorrect. I mean, when I say incorrect, I mean approximation of the final solution. Okay, so they grab this piece of text, they separate by tabs to jump and get some sentences. Class A of sentences, class B, with some labels. Shingles. Once we have the data, we can create our one hot. We build the shingles. We build the vocab. And then we go to the shingles. Shingle set vocab to build the one hot. And then we stack them. Okay. As before, we will compress our sparse vectors into dense signatures with min caching. Again, we will be using our NumPy implementation, which you can find the full code for here. By the way, guys, if my camera dies, it might be because of my battery, but like we're almost done here. So if it stops, then catch you after the China trip, which means on 26th of September. So that's gonna be like 10 days from now. Again, we'll be using NumPy, which you can find the full code here. Okay, so we go through the vectors and we get the signatures and we append the signatures and then we stack the signatures. So all the signatures have 100 dimensions. And so we've compressed our sparse from this length to this, a big difference. And then LSH. We'll use a Python dictionary here to hash and store our candidate pairs again. So we build the LSH, and then we go through the signatures and we add them to the LSH. So LSH, what LSH does is splits those vectors into bands and then maps them onto some index, I guess. It's important to know that our LSH buckets variable actually contains a separate dictionary for each band. we do not mix buckets between different bands. We see in our buckets the vector IDs, row numbers. So all we need to do is extract our candidate pairs, is loop through all buckets and extract pairs. Okay guys, I'm gonna stop here. This was roughly it. We can wrap this up later. I can paste the blog here. This was amazing blog. It's midnight here in Serbia. I have a couple more things to do before tomorrow. So I'll have to run. Awesome, guys. Okay, this is it. This is now 16th of September, 23rd day of streaming, building the OpenNLLB project. We learned a ton. We've done a ton of things. That's why we weren't just pushing to get the first checkpoint. We were trying to do this like as high quality as possible and learn a ton during the process. But like I think after China, it's going to be much faster because we've kind of I've built the muscles. I understand the whole code base. I understand pretty much all of the components of the pipeline. So I think it's gonna go much faster, limited by the compute, of course. And I'm gonna try and acquire some compute over the next couple of weeks. So we're gonna see how that goes. That's it, guys. Let's catch up after the China trip. I'm going to this Huawei conference, so hopefully I'm gonna learn a ton about what's going on in China, on the Chinese AI scene, and talk with researchers there about the stuff they're building. So let's see how that goes. I'm going to be reporting everything basically on my LinkedIn and Twitter, also in Discord, of course. So do check out like all of those posts and stuff. So yeah, cheers, guys. See you after roughly 9 days on 26th. Bye, guys. This was amazing series of 23 days of just working my ass off and building so much. Awesome. Thanks a lot, guys. Thank you, Josip. Thank you. Greetings from Greece. Thank you. And thanks. I don't know how to pronounce your name. VRGL. Let's go. Let's say Virgil. Thank you. Cheers, guys. Have a good night or a good day or good morning wherever you are. Bye.